This is the second collective episode in our journey through the roots of AI, as we delve into the fascinating era of the 1950s. Let us embark on this captivating exploration. 1950 Turing Test. Alan Turing's paper, titled Computing Machinery and Intelligence, published in 1950, is a seminal work that introduced the concept of the Turing test and raised fundamental questions about machine intelligence. In the paper, Turing explored the question of whether machines could exhibit intelligent behavior, and proposed a practical test to determine if a machine could be considered intelligent. To conduct the test, a typical setup involves three separate entities: the human evaluator, the machine, and the human confederate. The machine is usually a computer program or an AI system, while the human confederate is a person who participates in the test, pretending to be the machine's human counterpart. The evaluator communicates with both the machine and the human through a text-based interface, such as a computer terminal. During the test, the evaluator can ask any questions or engage in any conversation topics they desire. The machine and the human confederate respond to the queries, and the evaluator must make judgments solely based on their responses. The objective is for the machine to provide responses that are so human-like that the evaluator cannot reliably distinguish it from the human confederate. If the machine successfully convinces the evaluator that it is the human, it is considered to have passed the Turing test and demonstrated a level of intelligence comparable to human intelligence. However, if the evaluator consistently identifies the machine as the non-human participant, or if there is ambiguity in distinguishing between the machine and the human, the machine fails the test. Turing argued that the ability to imitate human intelligence in conversation is a reasonable criterion for determining machine intelligence. He also acknowledged the limitations of the test and recognized that it does not address questions of consciousness or internal mental states. The significance of Turing's work on computing machinery and intelligence is multifold. 1. Defining machine intelligence. Turing's paper provided one of the earliest attempts to define machine intelligence in a practical and measurable way. The Turing test became a benchmark for evaluating the capabilities of AI systems, and initiated the quest to develop machines that could exhibit human-like intelligence. 2. Philosophy of mind and AI. Turing's work sparked discussions and debates about the nature of the mind and whether machines can possess intelligence. It raised questions about the relationship between the mind and computation, and the possibility of achieving true understanding and consciousness through computational systems. 3. Practical implications for AI. The Turing test set a practical goal for AI researchers to develop conversational agents that could convincingly simulate human intelligence. It influenced the development of natural language processing, dialogue systems, and chatbots, as researchers sought to create machines that could pass the test. 4. Reflections on machine learning. Turing's paper also discussed the potential for machines to learn and improve their performance. He considered the idea of machine learning through trial and error and envisioned the possibility of machines that could acquire knowledge and skills over time. 5. Ethical and social implications. Turing's work raised important ethical and social considerations regarding the implications of creating intelligent machines. He discussed the possibility of machines exhibiting human-like behaviors and the potential impact on society, including concerns about the replacement of human labor and the responsibilities associated with creating intelligent entities. 6. Influence on AI research and development. Turing's ideas and concepts have had a profound impact on the development of AI as a field of study. The Turing test provided a tangible objective for AI researchers to strive for, shaping the research agenda and inspiring advancements in natural language processing, machine learning, and cognitive modeling. Turing's legacy. Beyond his contributions to AI, Turing's work on computing machinery and intelligence solidified his legacy as a visionary and pioneer in computer science. His ideas extended beyond AI and had far-reaching implications in cryptography, computer architecture, and theoretical computation. Turing's paper on computing machinery and intelligence remains a foundational work in AI and continues to stimulate debate and inspire research. It introduced the concept of the Turing test, provided a framework for evaluating machine intelligence, and influenced the direction and goals of AI research. Turing's work laid the groundwork for subsequent advancements in AI, leading to the development of intelligent systems capable of reasoning, learning, and interacting with humans. (1951) Game theory. Nash's game theory is a mathematical framework that analyzes decision-making in situations where multiple players interact. It was developed by American mathematician John Forbes Nash in the 1950s and 1960s, and has had a profound impact on various fields, including economics, political science, and artificial intelligence. We will explore the history and impact of Nash's game theory on AI. John Nash's groundbreaking work on game theory began with his doctoral dissertation at Princeton University in 1950, which introduced the concept of Nash equilibrium. Nash's equilibrium is a solution concept that describes a state in a game where no player has an incentive to unilaterally deviate from their chosen strategy, given the strategies of the other players. It provides a powerful tool for analyzing the outcomes and decision-making strategies in competitive situations. Nash's contributions to game theory gained recognition when he published his seminal paper, Non-Cooperative Games, in 1951. This paper introduced the concept of Nash equilibrium and provided the mathematical foundations for analyzing strategic interactions. Nash's ideas challenged the prevailing assumptions of cooperative game theory, which focused on cooperative outcomes and assumed that players could make binding agreements. Nash's non-cooperative approach allowed for a more realistic analysis of situations where players act independently and competitively. The impact of Nash's game theory on AI can be seen in various aspects. One of the most significant applications is in the field of automated negotiation. AI systems that negotiate with humans or other AI agents can utilize game-theoretic concepts, such as Nash equilibrium, to determine optimal negotiation strategies. By modeling the interaction as a game and seeking Nash equilibrium solutions, AI negotiators can make strategic decisions to maximize their own utility while considering the other party's preferences. Another area where Nash's game theory has influenced AI is in multi-agent systems. Multi-agent systems involve multiple autonomous agents interacting and making decisions. Game theory provides a formal framework to analyze the interactions between these agents and predict their behavior. By incorporating game-theoretic concepts, such as Nash equilibrium, AI systems can better understand and respond to the actions of other agents, leading to more effective coordination and decision-making. Nash's game theory has also played a crucial role in the development of AI algorithms for strategic reasoning. For example, in the field of reinforcement learning, which focuses on training AI agents to make optimal decisions through trial and error, game-theoretic approaches have been used to enhance the learning process. By modeling the interactions between agents as a game and seeking Nash equilibrium strategies, AI agents can learn to adapt and respond to the strategies employed by other agents in a competitive environment. Moreover, Nash equilibrium has been applied to address challenges in AI systems behavior modeling and prediction. By analyzing the strategic interactions among users, AI systems can anticipate their actions and adjust their responses accordingly. This is particularly relevant in recommender systems, where AI algorithms aim to suggest personalized content or products to users. By considering the user's preferences and anticipating their strategic behavior, AI recommender systems can improve the accuracy and relevance of their recommendations. Nash's game theory has also influenced the field of mechanism design in AI. Mechanism design involves designing rules and mechanisms that incentivize participants to act in desirable ways. Game theory provides a foundation for analyzing and designing mechanisms that achieve desirable outcomes, such as truthfulness and efficiency. By leveraging Nash equilibrium concepts, AI systems can design mechanisms that encourage participants to reveal their true preferences and maximize social welfare. In conclusion, Nash's game theory has had a significant impact on AI. Its concepts, particularly Nash equilibrium, have been instrumental in enhancing decision-making, negotiation, coordination, and behavior modeling in AI systems. By applying game-theoretic approaches, AI agents can analyze strategic interactions, learn from their environment, and make optimal decisions. Nash's game theory continues to shape the development of AI algorithms and systems, contributing to the advancement of intelligent and strategic AI agents. 1952 Checkers. Arthur Samuel's work on machine learning, particularly his development of a checkers playing program, is considered a landmark contribution to the field of AI. Samuel's research focused on creating systems that could learn from experience and improve their performance over time. In 1952, Samuel created a program that could play checkers, which became one of the earliest examples of machine learning. His program employed a learning algorithm that improved its gameplay by playing against itself, and adjusting its strategy based on the outcomes. Through repeated iterations, the program learned to make better moves and ultimately achieved a level of play that exceeded Samuel's own expertise. The program was written for the IBM 701 computer, which was one of the first commercial general-purpose digital computers. The program used a technique called temporal difference learning to improve its playing skill over time. Temporal difference learning is a type of reinforcement learning, which means that the program learns from its own actions and rewards. Samuel's approach involved using a state value function to evaluate the strength of different game positions in checkers. The state value function assigned a numerical value to each board configuration, indicating the desirability of that position for the player. The goal was to maximize the value of the final winning position. The key insight of temporal difference learning is that the value of a state can be updated based on the values of subsequent states, even without knowledge of the final outcome. This allowed the program to learn and improve through self-play. During training, the program would play many games against itself, starting from random positions. At each move, the program would select the move that maximized its chances of winning, based on the current state value function. As the game progressed, the program would update the state value function using a formula that combined the current estimate of the state's value with the estimate of the value of the next state. This update was called the temporal difference, because it measured the difference between the estimated value of the current state and the estimated value of the next state. By repeating this process over many games and iteratively updating the state value function, Samuel's program gradually improved its playing ability. The program learned to evaluate different board positions, recognize patterns, and make better decisions based on its past experiences. Over time, the program became a formidable checkers player, surpassing the capabilities of previous computer programs and even challenging human players. Samuel's work on temporal difference learning was a pioneering contribution to the field of reinforcement learning. It introduced the idea of learning from delayed rewards and laid the groundwork for subsequent advancements in this area, which have since become essential in various domains, including robotics, game-playing agents, and decision-making systems. The significance of Samuel's work in machine learning is multifold. 1. Early exploration of machine learning. Samuel's work was one of the earliest attempts to develop a machine that could learn from experience. His checkers program demonstrated that a machine could improve its performance through self-play and iterative adjustments, paving the way for future research in machine learning. 2. Reinforcement learning. Samuel's approach can be categorized as a form of reinforcement learning, a subfield of machine learning. His program used feedback in the form of game outcomes to reinforce or modify its strategies, an essential concept in reinforcement learning algorithms that are widely used today. 3. Autonomous learning. Samuel's program exhibited a degree of autonomy, as it was capable of learning and improving without explicit programming for each move. This autonomous learning aspect is a fundamental characteristic of modern machine learning systems, which can adapt and improve their performance based on data and experience. 4. Generalization and feature extraction. Samuel's work involved the extraction of features from the game state to guide the learning process. By identifying relevant patterns and features of the checkers board, his program could generalize its knowledge and make informed decisions. This notion of feature extraction and generalization remains a key aspect of machine learning algorithms. 5. Practical applications. Samuel's research on machine learning has had practical implications across various domains. The techniques and principles he employed in developing his checkers program, such as learning from experience and refining strategies over time, have been applied in areas such as game playing, pattern recognition, predictive modeling, and data analysis. 6. Influence on supervised learning. Samuel's work laid the foundation for supervised learning methods. Although his checkers program used self-play, it can be seen as a precursor to supervised learning, where a model learns from labeled examples provided by a human. Samuel's approach inspired subsequent research in supervised learning algorithms that rely on labeled datasets for training. 7. Inspiration for future research. Samuel's pioneering work inspired researchers to explore machine learning in various domains. His success in developing a checkers playing program fueled optimism and curiosity about the potential of machine learning, leading to advancements in neural networks, decision trees, reinforcement learning, and other machine learning techniques. 8. Importance of learning from data. Samuel's work underscored the significance of learning from data in AI systems. By enabling machines to learn from experience and adjust their behavior accordingly, Samuel highlighted the importance of data-driven approaches in creating intelligent systems. Arthur Samuel's work on machine learning set the stage for subsequent research in this field. His checkers playing program demonstrated the potential of machines to learn and improve their performance through iterative feedback and experience. Samuel's contributions to autonomous learning, reinforcement learning, generalization, and feature extraction have shaped the development of machine learning algorithms, and inspired researchers to explore the applications of learning from data across diverse domains. His work continues to be regarded as a landmark achievement in the field of AI and remains foundational to the advancement of machine learning. 1955 Logic Theorist. The logic theorist, developed by Alan Newell and Herbert A. Simon in 1955, was one of the earliest AI programs and a groundbreaking achievement in the field. It was the first program capable of proving mathematical theorems from the field of symbolic logic. The logic theorist was designed to mimic the problem-solving strategies of human mathematicians. It operated by applying logical rules and inference techniques to a set of axioms, and attempting to derive new theorems through a process of symbolic manipulation. The logic theorist operated by employing a set of transformation rules derived from the work of mathematician David Hilbert, and his formal proof system. It would start with a set of axioms and use these transformation rules to manipulate the logical statements, until it reached the desired theorem or a contradiction. To guide its search for a proof, the logic theorist utilized heuristic techniques. It employed a measure called information content to evaluate the progress made towards the desired theorem at each step. This measure quantified the information gained from applying a transformation rule to a particular logical statement. The concept of information content was based on the notion that each transformation rule applied to a logical statement would reduce the complexity, or size of the statement. The greater the reduction in complexity, the more information was gained. When the logic theorist applied a transformation rule to a statement, it would generate one or more new statements. The information content of the resulting statements was compared to the original statement. If the resulting statements had lower information content, it indicated progress towards a proof. To calculate the information content, the logic theorist used a heuristic measure that assigned values to different types of transformations based on their expected effectiveness. These values were predetermined based on human intuition and knowledge of logical reasoning. For example, a transformation rule that simplified the statement significantly would be assigned a higher value than a rule that made a minor modification. The information content measure served as a guide for the logic theorist's search algorithm. It would prioritize applying transformation rules that were expected to yield the highest reduction in information content, as they were considered more likely to lead to a proof. By focusing on rules that reduced complexity, the program aimed to steer the search towards a more concise and elegant solution. The use of information content in the logic theorist demonstrated the importance of heuristic measures in guiding the search for a solution in complex problems. By evaluating the impact of each transformation based on the reduction in complexity, the program could make informed decisions about which rules to apply and in what order, ultimately leading to more efficient and effective theorem proving. Newell and Simon implemented the logic theorist on the IBM 704 computer, which was a cutting-edge machine at the time. They tested the program's capabilities by having it prove a selection of theorems from Whitehead and Russell's Principia Mathematica, a monumental work in symbolic logic. The logic theorist's main achievement was its ability to prove mathematical theorems that were challenging and required non-trivial reasoning. The significance of the logic theorist in the development of AI is multifold. 1. Demonstration of automated reasoning. The logic theorist demonstrated that computers could perform complex reasoning tasks that were traditionally reserved for human mathematicians. It showcased the potential of AI systems to automate problem-solving and theorem-proving in formal logical systems. 2. Heuristic search and problem-solving. The logic theorist introduced the use of heuristic search algorithms and problem-solving heuristics in AI. By employing heuristics to guide its search through the space of possible theorem proofs, The program demonstrated the value of intelligent search strategies for efficient problem solving. 3. Symbolic manipulation and logic. The logic theorist highlighted the importance of symbolic manipulation and logic in AI. It showed that intelligent behavior could be achieved through symbolic reasoning, where expressions and rules of logic are manipulated to derive new knowledge. 4. Development of symbolic AI. The logic theorist contributed to the emergence of symbolic AI, which focuses on representing and manipulating knowledge using symbols and formal logic. Symbolic AI became a dominant paradigm in early AI research, and the logic theorist served as a precursor to subsequent AI programs that used symbolic reasoning. 5. Influence on cognitive science. The logic theorist had a significant impact on the field of cognitive science. It influenced researchers in the cognitive psychology community, who sought to understand and model human problem-solving and reasoning abilities. The program provided insights into human cognition and inspired the development of cognitive architectures. 6. Development of Newell and Simon's general problem solver. The logic theorist served as a precursor to Newell and Simon's later work on the general problem solver, GPS. The GPS was a more general-purpose problem-solving system that applied the principles and techniques developed in the logic theorist to a broader range of problems. The GPS laid the foundation for subsequent research in AI planning and problem-solving. Overall, the logic theorist was a significant achievement in the early days of AI. It demonstrated the potential of computers to perform complex reasoning tasks, introduced heuristic search algorithms and problem-solving heuristics, and contributed to the development of symbolic AI. The program's impact extended beyond AI, influencing cognitive science and inspiring further research in automated reasoning and problem-solving. The logic theorist remains an important milestone in the history of AI, showcasing the power of intelligent systems to tackle challenging intellectual tasks. 1956 Dartmouth Conference. The Dartmouth Conference, held in the summer of 1956, is widely regarded as the birth of artificial intelligence as a formal field of study. The conference was organized by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, who brought together a group of researchers to explore the possibilities of creating machines that could simulate human intelligence. A summary of what some of the attendees contributed to the conference is: 1. John McCarthy was the organizer of the conference, and he also gave a keynote address. He provided a vision for the future of AI, and he argued that it was possible to create machines that could think. 2. Marvin Minsky was a co-organizer of the conference, and he also gave a keynote address. He discussed the mathematical foundations of AI, and he argued that AI could be used to solve a wide range of problems. 3. Claude Shannon gave a presentation on the mathematical theory of communication, which is a foundation for AI. He also discussed the potential applications of AI, and he argued that AI could be used to improve communication and understanding. 4. Nathaniel Rochester gave a presentation on the problem of machine learning, which is a central problem in AI. He argued that machine learning was essential for the development of AI, and he proposed a number of new approaches to machine learning. 5. Alan Newell and his colleague Herbert A. Simon presented their work on the logic theorist, one of the first AI programs. The logic theorist was able to prove theorems in logic, and it demonstrated that AI was capable of solving complex problems. 6. Herbert A. Simon gave a presentation on the theory of bounded rationality, which is a theory of how humans make decisions. He argued that AI could be used to model human decision-making, and he proposed a number of new approaches to AI. 7. Oliver Selfridge gave a presentation on his work on machine vision. He developed the pandemonium model of machine vision, which is still used today. 8. Raymond Solomonoff gave a presentation on his work on universal induction, which is a foundation for machine learning. He argued that universal induction could be used to develop AI systems that could learn from data. The Dartmouth Conference was a seminal event because it marked the first time that AI was defined as a distinct field, with its own objectives and research agenda. During the conference, John McCarthy, who coined the term artificial intelligence, outlined the goals and scope of AI research, setting the stage for decades of exploration and advancements in the field. The conference attendees, including mathematicians, computer scientists, and psychologists, discussed a wide range of topics related to AI, such as problem solving, learning, natural language processing, and perception. They aimed to develop computational models and algorithms that could replicate or simulate human cognitive abilities. One of the key objectives of the Dartmouth Conference was to build intelligent machines capable of exhibiting human-like intelligence. The researchers envisioned creating programs that could understand natural language, solve complex problems, learn from experience, and reason logically. Although the conference was ambitious in its goals, the attendees recognized the challenges and limitations of AI research at the time. They acknowledged that creating a fully intelligent machine would require significant advancements in computing power, algorithms, and knowledge representation. Despite the ambitious goals and the challenges ahead, the Dartmouth Conference had a profound impact on the development of AI for several reasons. 1. Definition and scope of AI. The conference led to the formal definition of AI as a field focused on creating machines that can exhibit human-like intelligence. It established AI as a distinct research discipline and set the agenda for future research and development in the field. 2. Collaboration and community building. The conference brought together researchers from different disciplines and fostered collaboration and exchange of ideas. It established a sense of community among AI researchers, which was vital for sharing knowledge, discussing challenges, and advancing the field collectively. 3. Research direction and subfields. The discussions at the Dartmouth Conference helped shape the research direction of AI. It led to the emergence of subfields within AI, such as machine learning, natural language processing, computer vision, and expert systems, which became the focus of subsequent research and development efforts. 4. Public awareness and funding. The Dartmouth Conference raised public awareness about AI and its potential impact on society. It captured the attention of the media and government agencies, leading to increased funding and support for AI research. This attention helped create a conducive environment for the growth of the field. 5. Inspiration and inspiration. The Dartmouth Conference inspired generations of researchers, students, and entrepreneurs to pursue AI research and development. The ideas and discussions at the conference served as a catalyst for groundbreaking advancements in AI in the subsequent years, and continue to inspire and guide AI research today. It is important to note that while the Dartmouth Conference played a pivotal role in the development of AI, it also had its limitations. The researchers at the conference had ambitious goals but underestimated the complexity and challenges involved in achieving human-like intelligence. Progress in AI has been gradual and incremental, with significant breakthroughs and advancements occurring over time. In conclusion, the Dartmouth Conference was a landmark event that marked the birth of AI as a field of study. It defined the objectives and scope of AI research, brought together a community of researchers, and set the agenda for future advancements. The conference sparked enthusiasm and laid the groundwork for subsequent research and development efforts in AI, shaping the field's trajectory and influencing its growth and impact on society. 1957 General Problem Solver. The General Problem Solver, GPS, was a landmark achievement in the field of artificial intelligence, AI, developed by Alan Newell and Herbert A. Simon in 1957. The GPS was an early attempt to create a general-purpose problem-solving system that could tackle a wide range of problems by applying a set of heuristics and problem-solving techniques. The GPS was designed to mimic human problem-solving strategies and aimed to solve problems in a logical and systematic manner. It operated by representing problems and their associated knowledge in a symbolic form, and applied problem-solving rules to manipulate these symbols. One of the key innovations of the GPS was the use of means-ends analysis, a problem-solving strategy that involves identifying the differences between the current problem state and the desired goal state, and applying operators to reduce these differences. Means-ends analysis is a problem-solving approach that involves breaking down a complex problem into smaller subgoals or subproblems, and then identifying the means or actions that can be taken to bridge the gap between the current state and the desired goal state. The system works by comparing the current state of the problem with the desired goal state, and formulating subgoals that would reduce the difference between the two states. The program uses operators or rules to manipulate the problem state, moving from one state to another through a series of actions. Means-ends analysis is used to select and apply operators that are most likely to lead to the desired goal state. It involves continuously monitoring the progress made toward the goal, detecting obstacles or barriers, and making appropriate adjustments to the problem-solving strategy. By applying means-ends analysis, GPS can iteratively refine its approach, breaking down the problem into manageable steps and gradually reducing the difference between the current state and the desired goal state, until the problem is solved or a solution is reached. The means-ends analysis in the context of GPS involves the following steps. 1. Problem decomposition. Means-ends analysis starts by decomposing a complex problem into smaller, more manageable subgoals. These subgoals represent intermediate states that, when achieved, bring the system closer to the final goal state. By breaking down the problem into subproblems, GPS can focus on addressing specific aspects of the problem and simplify the overall problem-solving process. 2. Difference reduction. Once the subgoals are identified, means-ends analysis focuses on reducing the difference or gap between the current state and the desired goal state. It analyzes the problem state and determines the main obstacles or differences that prevent the system from reaching the goal state directly. 3. Operator selection. GPS employs a set of operators or rules that define the actions that can be performed on the problem state. These operators represent possible steps or actions that can be taken to modify the problem state and bring it closer to the goal state. Means-ends analysis involves selecting the most suitable operator based on its potential to reduce the difference between the current state and the goal state. The system evaluates the operators based on their relevance, effectiveness, and efficiency in achieving the desired outcome. 4. Subgoal ordering. In means-ends analysis, the system determines the order in which the subgoals should be pursued. It considers the dependencies and relationships between the subgoals to create a plan or strategy for achieving the desired goal state. the ordering of subgoals ensures that each subgoal is addressed in a sequence that maximizes progress toward the overall goal. 5. Monitoring and adjustments. As the problem-solving process unfolds, GPS continuously monitors the progress made toward the goal state. It checks whether the selected operators are leading to the desired outcomes or if there are unexpected barriers or obstacles. If obstacles are encountered, the system adjusts its strategy by selecting alternative operators or modifying the order of subgoals. This iterative process allows GPS to adapt and refine its problem-solving approach based on the feedback received during execution. Means-ends analysis, as employed by GPS, provided a framework for systematic problem-solving by breaking down problems into manageable parts, defining subgoals, selecting relevant operators, and iteratively reducing the difference between the current state and the desired goal state. This approach laid the foundation for subsequent developments in problem-solving and planning within the field of artificial intelligence. The GPS was also notable for its ability to learn from experience and adapt its problem-solving strategies. It employed a form of trial and error learning, where it would try different problem-solving approaches and evaluate their success. Based on this evaluation, the GPS would modify its problem-solving techniques and heuristics to improve its future performance. The trial and error method worked in GPS as follows. 1. Operator application. GPS utilized a set of predefined operators or rules that defined the possible actions that could be applied to the problem state. These operators were designed to modify the problem state and move it closer to the goal state. In the trial and error method, GPS would randomly select an operator and apply it to the current problem state, without any prior knowledge of its effectiveness. 2. State evaluation. After applying an operator to the problem state, GPS evaluated the resulting state to determine whether progress had been made towards the goal state. The system compared the new state with the desired goal state and assessed the difference or discrepancy between them. 3. Backtracking and retry. If the applied operator did not lead to a reduced difference between the current state and the goal state, GPS would backtrack and retry a different operator. The system would undo the changes made by the unsuccessful operator and try another operator from the available set. 4. Iterative exploration. GPS repeated this process of applying operators, evaluating the resulting states, and backtracking until a solution was found or until a termination condition was met. The system explored different operators in a trial and error manner, learning from unsuccessful attempts and refining its search based on the feedback received. 5. Problem-specific knowledge. Although trial and error was a general technique used in GPS, the system could also leverage problem-specific knowledge to guide the search process. For example, if the problem domain provided some heuristics or hints about potentially successful operators, GPS could prioritize or bias its trial and error exploration based on that information. The trial and error method in GPS allowed the system to explore the problem space, test different operators, and gradually refine its search until a satisfactory solution was found. It provided a flexible approach to problem solving, albeit without the efficiency and guidance provided by more advanced search algorithms and problem-solving techniques developed in subsequent years. The significance of the GPS in the development of AI is multifold. 1. General problem-solving approach. The GPS introduced a general problem-solving approach that could be applied to a wide range of problems. It demonstrated that a single problem-solving system could be designed to tackle diverse problem domains, showcasing the potential of AI systems to exhibit general intelligence. 2. Heuristics and problem-solving techniques. The GPS popularized the use of heuristics and problem-solving techniques in AI. It showcased the importance of intelligent search strategies, means-ends analysis, and hierarchical goal decomposition in efficient problem-solving. 3. Symbolic representation and manipulation. The GPS emphasized the use of symbolic representation and manipulation of knowledge. It highlighted the power of representing problem states and operators as symbols, and manipulating them using logical operations and rules. 4. Learning and adaptation. The GPS demonstrated the ability of AI systems to learn from experience and adapt their problem-solving strategies. Its trial-and-error learning approach allowed the GPS to improve its performance over time by modifying its heuristics and techniques based on feedback. 5. Influence on problem-solving research. The GPS had a significant impact on subsequent research in problem-solving and planning in AI. Its techniques and principles became foundational for the development of more advanced problem-solving systems, planning algorithms, and decision-making frameworks. 6. Cognitive science and human problem-solving. The GPS influenced the field of cognitive science by providing insights into human problem-solving processes. Its emphasis on symbolic representation, means-ends analysis, and hierarchical goal decomposition inspired researchers studying human cognition and problem-solving. 7. Development of AI planning. The GPS laid the foundation for the development of AI planning, a subfield of AI that focuses on automatically generating plans or sequences of actions to achieve goals. The principles and techniques introduced by the GPS became integral to subsequent research in AI planning. The General Problem Solver, GPS, was a significant contribution to AI, showcasing the potential of general problem-solving systems and the importance of heuristics, symbolic representation, and learning in AI research. The GPS influenced subsequent advancements in AI, including planning systems, decision-making frameworks, and cognitive models of human problem-solving. Its impact on the field continues to be felt, as it shaped the development of AI systems that can tackle complex problems in a logical and systematic manner. 1957 K-means clustering. K-means clustering is a widely used unsupervised machine learning algorithm that partitions data into distinct groups based on their similarity. It is a simple yet powerful algorithm that has been instrumental in various fields, including data mining, image processing, and pattern recognition. We will delve into the intricacies of K-means clustering, its underlying principles, and notable contributions made by authors in its development. 1. The concept of K-means. K-means clustering was first introduced by Stuart Lloyd in 1957, but its significance was later popularized by James McQueen in 1967. The algorithm's objective is to partition a given dataset into K distinct clusters, where each data point is assigned to the cluster with the nearest mean, centroid, based on a distance metric, typically the Euclidean distance. 2. The K-means algorithm. The algorithm follows a simple iterative process to achieve its goal. Initially, K-centroids are randomly initialized. Then, in an iterative manner, the algorithm assigns each data point to the nearest centroid and recalculates the centroids based on the newly assigned points. This process continues until convergence, where the centroids no longer shift significantly or a predefined number of iterations is reached. 3. Objective function and optimization. K-means clustering minimizes the sum of squared distances between data points and their assigned centroids, often referred to as the within-cluster sum of squares, WCSS, or the distortion. By minimizing this objective function, the algorithm aims to ensure that data points within the same cluster are more similar to each other than to those in other clusters. 4. Initialization methods. The initial placement of centroids significantly impacts the final clustering result. Several initialization methods have been proposed to address this issue. One popular approach is the 4G method, introduced by William Lloyd in 1982, where k data points are randomly selected as initial centroids. Another method, proposed by McQueen, involves iteratively updating the initial centroids using a subset of the data until convergence. 5. Challenges and variants of k-means. K-means clustering is not without its limitations. One significant challenge is its sensitivity to the initial centroid placement, which can lead to suboptimal solutions. To overcome this, various variants and enhancements have been proposed. For instance, the k-means plus algorithm, introduced by David Arthur and Sergei Vasilvitsky in 2007, improves centroid initialization by considering the probability distribution of each data point based on their distances to already chosen centroids. 6. Handling large datasets. As datasets grow in size, the traditional k-means algorithm can become computationally expensive. To address this issue, researchers have developed scalable versions of k-means clustering. One notable example is the scalable k-means plus algorithm proposed by Barman-Barmani et al. In 2012, which employs efficient sampling techniques to accelerate the centroid initialization process for large datasets. 7. Evaluation and validity measures. Assessing the quality and validity of clustering results is crucial. Various metrics and indices have been developed to evaluate the performance of k-means clustering, including the silhouette coefficient, the Dunn index, and the Davies-Baldwin index. These measures provide insights into the compactness, separation, and overall quality of the clusters. 8. Applications of k-means. K-means clustering finds applications in diverse fields. In data mining, it is used for customer segmentation, anomaly detection, and market segmentation. In image processing, k-means is employed for image compression, image segmentation, and object recognition. Additionally, it has been applied in text mining, bioinformatics, and recommendation systems, among others. K-means clustering, originally introduced by Stuart Lloyd and popularized by James McQueen, is a fundamental algorithm in unsupervised machine learning. Its ability to partition data into distinct groups based on similarity has made it invaluable in various domains. Over the years, researchers have made significant contributions to the algorithm, addressing challenges and proposing enhancements. From initialization methods to scalability and evaluation measures, the development of k-means clustering has been driven by the need to extract meaningful patterns from data. As technology advances and datasets grow larger, k-means clustering and its variants will continue to play a vital role in uncovering valuable insights and facilitating data-driven decision-making. 1958 – The Computer and the Brain. John von Neumann's book, titled The Computer and the Brain, was published posthumously in 1958. In this book, von Neumann explored the analogy between computers and the human brain, laying the foundation for the study of computational neuroscience and the relationship between artificial and biological intelligence. Von Neumann's book delves into the idea that the brain can be seen as a computing machine, with information processing occurring through the interaction of neurons and their connections. He examined the similarities in the logical structure and information processing capabilities of computers and the brain, providing insights into the potential of computers to emulate or simulate cognitive processes. The book is divided into two parts. The first part, The Computer, discusses the basic principles of computation, including the von Neumann architecture, which is still the standard for computer design today. The second part, The Brain, discusses the anatomy and physiology of the brain, and how it can be viewed as a computing machine. Von Neumann argues that the brain is a massively parallel processor, and that it uses a variety of techniques to store and retrieve information. Although von Neumann was unable to complete the book before his passing, his wife, Clara Dan von Neumann, edited and published it posthumously. The book has since been translated into several languages and is widely regarded as a seminal work in the field of artificial intelligence. Its insights into the similarities between computers and the human brain continue to inform and inspire researchers in the field today. The significance of von Neumann's work on the computer and the brain is multifold. 1. Relationship between computers and the brain. Von Neumann's book initiated a discussion on the parallels between computers and the human brain. It highlighted the notion that the brain operates through information processing and computational principles, paving the way for further exploration into the study of computational neuroscience. 2. Information processing and computation. Von Neumann's work emphasized the role of information processing and computation in understanding both artificial and biological systems. He argued that the brain processes and manipulates information in a manner similar to how computers do, suggesting that computation could serve as a basis for modeling and understanding cognitive processes. 3. Cognitive architecture. Von Neumann's book contributed to the development of cognitive architectures, by proposing that the brain operates through a hierarchical structure of functional units. He suggested that the brain's organization resembles the layered architecture of early computer systems, with each layer responsible for specific functions. 4. Impact on AI and cognitive science. Von Neumann's ideas influenced the fields of AI and cognitive science by providing a framework for studying and modeling intelligent behavior. His exploration of the brain-computer analogy spurred research on creating computational models of cognitive processes, and understanding the relationship between artificial and human intelligence. 5. Early neural network research. Von Neumann's book laid the groundwork for early research on neural networks. His examination of the brain's structure and information processing capabilities inspired subsequent work on artificial neural networks, which aimed to simulate the behavior of interconnected neurons in computational models. 6. Future directions. Von Neumann speculated on the potential future development of computers and their impact on society. He anticipated the emergence of more powerful computers capable of advanced computations, and their potential to revolutionize various fields, including AI, scientific research, and societal decision-making. 7. Legacy in computer science. Beyond its influence on AI and cognitive science, von Neumann's book solidified his legacy as a prominent figure in computer science. His contributions to the development of computer architecture, information theory, and the theory of self-replicating systems have had a lasting impact on the field. The computer and the brain continues to be relevant in the study of AI and computational neuroscience. Von Neumann's insights into the brain-computer analogy, information processing, and cognitive architectures provided a theoretical foundation for subsequent research in these areas. His work inspired the development of computational models of cognition, neural networks, and advanced computer systems. Von Neumann's exploration of the relationship between computers and the brain expanded our understanding of both artificial and biological intelligence, shaping the trajectory of AI research and its applications. 1958 Perceptron. The perceptron, developed by Frank Rosenblatt in 1958, was one of the earliest artificial neural networks capable of learning. It played a crucial role in the early development of AI and machine learning. The concept of the perceptron was inspired by the structure and functionality of biological neurons in the human brain. The perceptron aimed to mimic the way neurons process information by using a mathematical model. It consisted of a single layer of artificial neurons, known as perceptrons, which were interconnected with weighted connections. These perceptrons were binary classifiers, taking in multiple inputs and producing a single output. Frank Rosenblatt's perceptron algorithm was based on a mathematical model of a single neuron in the brain. The algorithm uses a linear threshold function to determine the output value of the perceptron. The threshold function takes the weighted sum of the inputs and applies a threshold value to determine the output. If the output value is below the threshold, the perceptron outputs a 0, and if it is above the threshold, it outputs a 1. The perceptron algorithm can be used for binary classification problems. It learns to differentiate between two classes of patterns by adjusting its weights until it can correctly classify all the input examples. The perceptron algorithm can also be used for multi-class classification problems by using multiple perceptrons. Each perceptron is trained to recognize one class of patterns, and the output of all the perceptrons is combined to produce the final classification. Each input to the perceptron was associated with a weight, which determined the significance or importance of that input. The perceptron computed a weighted sum of the inputs, and then applied an activation function to determine the output. The activation function served as a threshold, determining whether the perceptron would fire or remain inactive based on the computed sum. During the learning phase, the perceptron adjusted its weights based on a learning rule, known as the perceptron learning rule or delta rule. The learning rule aimed to minimize the difference between the predicted output of the perceptron and the desired output, using a form of supervised learning. By iteratively adjusting the weights based on the learning rule, the perceptron could gradually improve its ability to classify inputs correctly. The perceptron's learning algorithm allowed it to learn linearly separable patterns. It could classify inputs into two categories or classes by drawing a decision boundary in the input space. This boundary was defined by the weights and biases of the perceptron, which determined its discriminative power. However, the perceptron was limited to learning linearly separable patterns, and could not handle more complex patterns that required non-linear decision boundaries. Despite its limitations, the perceptron attracted significant attention and sparked optimism about the potential of neural networks and AI. Its successful application to problems like character recognition and pattern classification showcased its capabilities. However, the limitations of the perceptron, as outlined in a book titled Perceptrons, by Marvin Minsky and Seymour Papert in 1969, dampened some of the initial enthusiasm. Minsky and Papert's book demonstrated the limitations of the perceptron by proving that it could not learn certain logical functions that required non-linear decision boundaries. They showed that the perceptron learning algorithm would fail to converge and would keep adjusting weights indefinitely in such cases. This revelation led to a decline in interest and funding for neural networks and AI research, an era that came to be known as the AI winter. Nonetheless, the Perceptron remains a landmark contribution to AI and machine learning. It laid the foundation for subsequent developments in neural networks, inspiring researchers to explore more complex architectures capable of handling nonlinear patterns. The Perceptron's significance extended beyond its immediate capabilities, as it prompted the exploration of more sophisticated algorithms and architectures that addressed its limitations, leading to the resurgence of neural networks and the field of deep learning decades later. In summary, the Perceptron, developed by Frank Rosenblatt, was an early artificial neural network that could learn and make binary classifications. Its learning algorithm, based on adjusting weights, allowed it to improve its classification accuracy. While it had limitations in handling nonlinear patterns, the Perceptron's impact on the field of AI and machine learning was profound, paving the way for further advancements in neural networks and inspiring researchers to overcome its limitations.